This is multivariable calculus, and in this video I'm going to talk about section 15.6, surface area. So in the last section we started talking about applications of double integrals, and we spent a lot of time talking about mass, center of mass, moment of inertia. So we've got another application today. It's surface area, which is relatively simple. So this is going to be a pretty quick video. I'm going to leave out a lot of the details on solving the integrals out because at this point I'm going to assume that those integration techniques are things that you know how to do. So we're primarily going to focus on the setup. I'm not going to go into a full derivation because we're going to go through it in class, but let's just talk a little bit about what we're doing here. So what we're talking about is having a function that's typically going to be z as a function of x and y, and that's going to define some surface. And what we're trying to do is we're trying to find the surface area. And when we find the surface area, it's going to be sort of like when we were doing arc length back in calculus BC. So in 3 dimensions, what we're going to do is we're going to break our surface into a bunch of smaller regions. And we're going to assume those regions, we're going to call them subrectangles. In reality, they're going to be small parallelograms, but we're going to end up breaking it into a bunch of small subregions, and we're going to treat those as planar surfaces. And then we're just going to take a bunch of those small subregions and we're going to add them together to create the overall surface area. If you think back when we did arc length in 2 dimensions, to get the length of the curve, we broke the curve into a bunch of really, really small line segments, and then we used an integral to add up all those line segments. So we're going to do the same thing here. We're going to use a double integral to add up all of these subregions. Okay, so when we set this up, it's fairly easy to do. And this part right here where I've got this diagram, I'm going to spend a little bit of time going through this in class. We're going to talk about the derivation of where this comes from. But just keep in mind that this is in a lot of ways very, very similar to arc length in 2 dimensions. Okay, so to find the area of my surface then, I'm going to take the limit as m and n approach infinity. And I've got 2 summations here from I is 1 to m, from j is 1 to n, and then I'm essentially saying delta t is the area of that subregion. And then we're just going to add all of those together. So instead of writing it in summation notation, we're going to write it as a double integral. Now, this is the part that's going to seem a little bit like magic right now because I'm not going through the derivation, but this is how we're actually going to set this up. And what we have is the double integral over our region, and we've got the square root of the x partial derivative squared plus the y partial derivative squared plus 1. So where that radicand comes from is a little bit complicated from an algebraic standpoint, but it's actually fairly simple because we're going to use the area of a parallelogram using 2 vectors, and then we're going to simplify it down and it's going to become that value there. So we'll talk about that in class. But if you notice, this sort of looks like what the integrand looked like, the radicand looked like when we were doing arc length. So with arc length, we had 1 plus dy dx squared, and then we would integrate over, whatever the region was. Well, it's the same idea here. So we've got a double integral, but now we have the x partial squared plus the y partial squared plus 1. Okay, so we can think of this as the x partial and the y partial, or we can write it in another form, as you can see down here. You can see down below, we've got this written as del z del x squared plus del z del y squared. Same thing, it's just different notation. Okay, so that's really the main idea. And like I said, the derivation part of this is what we're going to go through in class. So what we're going to do the rest of the time here is just apply this, which if you just look at it from this standpoint, it's essentially just a formula. So the challenge here is not so much the setup. The challenge on a lot of these is going to be actually executing the double integral and getting the solutions. So on a lot of these problems, you're going to be asked to get exact solutions, which means you have to work all the way through the double integral. Okay, so let's take a look at an example here. So it says, find the surface area of the portion of the surface z is equal to the square root of 4 minus x squared that lies above the rectangle R in the xy plane whose coordinates satisfy this domain. So we're going from 0 to 1 on the x and 0 to 4 on the y. Okay, so if we want to do this, we're going to need to know our partial derivatives. So we're going to need to know del z del x. We're going to need to know del z del y. Well, the nice thing here is del z del y is going to be 0, but let's just do our general setup here. Our surface area is going to be the double integral over our region, and that would be then the square root of del z del x squared plus del z del y squared plus 1. And then we're just going to call this for now the differential dA. And now we're going to convert this into a double integral. Okay, so remember, you can look at this equation. It's pretty easy to see that del z del y is going to be 0, but there is a little bit of setup here that we have to do, because we have to know what del z del x is. All right, so I'm not going to go through all the steps for del z del x, but you can tell pretty easily here that del z del x is going to end up being negative x over the square root of 4 minus x squared. Okay, so pretty easy to get that partial derivative. All right, so now let's set up our double integral. And like I said before, I'm not going to go through all the steps on these, but we'll talk about the setup. We'll kind of talk about what the idea is, but I'm not going to work through all these steps because you guys have done a lot of double integrals at this point. So I'm going to choose to integrate with respect to x first. And the reason I'm going to do that is because I really only have x in this expression. I'm going to end up with the square root of, when I square del z del x, I'm going to get x squared over 4 minus x squared plus 1. And I'm going to do dx dy here. And in the x direction, I'm going from 0 to 1. In the y direction, I'm going from 0 to 4. And that would be my setup. Now, the rest of this is, like I said, it's a little more complicated from an integration standpoint because I have to kind of stop and think about how I'm going to do this. But what you can do on this one is you can actually get a common denominator between these two terms. And then it turns out you can use an inverse sign and you can integrate this. It's fairly simple to do. But in the end, you're going to end up with 4 pi over 3 here as an exact solution. Okay, so like I said, the setup part of this is fairly simple because all we need to know is the partial derivative with respect to x, the partial derivative with respect to y, essentially plug into a formula. And then, like I said before, the challenge then is how do we get the exact solution from the double integral? Okay, so let's take a look at another one here. So the next one, it says find the surface area of the portion of the paraboloid z equals x squared plus y squared below the plane z is equal to 1. Now, this is a little more complicated from the standpoint of I have to think about what my domain is in this scenario, and I also have to think a little bit about how is my setup going to relate to the shape that I'm dealing with for my domain. Okay, so let's start with the fact that we know we're doing surface area, so we know we're going to need partial derivatives. So del z del x, pretty clearly here is 2x. Del z del y is going to be 2y. Okay, and now let's think about what our domain looks like. If we have the plane z equals 1, and we're looking at a paraboloid z equals x squared plus y squared, when I get to the point where z is equal to 1, I'm looking at a circle, x squared plus y squared equals 1. So if I were to project that circle down into the xy plane, that's essentially the region that I'm going to integrate over. Okay, so let's go into the setup here. So I know my surface area is going to be the double integral over this region. And we're going to have the square root of 2x squared plus 2y squared, so essentially 4x squared plus 4y squared plus 1, and then dA. And now I've got to think about, okay, how do I want to actually go through and set this up? All right, so Remember, we were talking about the idea that we're essentially integrating over a circular region, which immediately for me makes me think of polar coordinates. And so what I'm going to do here is I'm going to convert this into a polar coordinate setup. So I know I've got an entire circle, x squared plus y squared is equal to 1. So I know from the theta perspective, I'm going to go from 0 to 2 pi. I've got a circle with a radius of 1, so I'm going to go from 0 to 1 for the radius. 4x squared plus 4y squared is the same as 4r squared. And then I'm going to have my r dr d theta. So what you're going to have to think about on these problems, you can see I just sort of jumped right into it. Sometimes you're going to have to think about what's the best approach to take. And there's not necessarily a right way or a wrong way to do these, but sometimes one method might be easier than the other. Using rectangular coordinates sometimes will be easier. Using polar coordinates sometimes will be easier. Once you've gotten to that point, it's pretty clear here. I'm going to do a substitution with the r part of the integral, and then I'm going to end up multiplying by 2 pi. So in the end, if you want to try to solve this one out, you would end up with 1/6 pi times 5 root 5 minus 1. Okay, so again, not really focusing on the techniques of solving the double integral, but more about the setup here and more about really thinking about with the setup, what's my best approach when I actually decide it's time to solve that double integral. All right, so I've got one more example here. And this last one, I want to show you the setup and talk a little bit about solution techniques here, because again, with these double integrals and getting exact solutions, these can get kind of tricky. Okay, so let's talk about this example and just go through some of the setup and steps that you would use if you were going to find an exact solution. So the first thing that I'm going to do here, just like always, is I'm going to get my partial derivatives. So I'm going to get my partial with respect to x. Del z del x in this case would be 2x plus 1. And del z del y would be equal to just 1 in this case. So when I set up my integral here, since this is a rectangular region, this is pretty easy to set up. I'm just going to choose to integrate with respect to x first. And when I do that, what I'm going to end up with is this integral. So I'm going to go from -1 to 1 on the y. And my integrand would be 2x plus 1 squared plus 1 squared plus 1. And then I'd have dx dy. Okay, so what I'm going to do here then is I'm going to think about a trig substitution for this. And let me explain how I would do that. So I've still got this same integrand, except for I'm going to write it in a slightly modified form. And what I'm going to have here is 2x plus 1 squared plus 2. Then I'll have my dx dy. So from a trig substitution standpoint, what I would end up with is essentially a u squared plus a squared situation. So what I could do here is I could say, all right, for this situation, my u is going to be 2x plus 1. And then my a value would be the square root of 2. So I can think of square root of 2 squared. This is like my a squared here, and this is like my u squared here. And then from there, you can use your trig substitution. It's a little bit of a difficult process, but you can go through that process and you can solve it out, and then you can get the exact solution. So the thing is, it can be done, but it can be kind of challenging. So here, this trig substitution is not terrible. Once you get through the substitution, it's not too bad, but it does require some advanced integration skills, and it requires a lot more effort than what we were talking about before with, once we get to this point, since we've got a variable, or excuse me, an integrand with just a single variable, we can easily split this apart into 2 single integrals and just solve it out from there. Okay, so in the end here, if you got the exact solution, here's what you would end up with. So I'll write my solution over here to the side since I'm running a little bit out of space. But my exact solution, it's a little messy, which gives you a good indication of how this was a little bit difficult to do by hand. So I got 3 root 11 plus the natural log, and then I've got a ratio in here, 3 over root 2 plus root 11 halves, and then that's divided by negative 3 over root 2 plus root 11 halves. And I've got my bracket over there. So that would be my exact solution. And again, you don't need to try to solve these things out this way, but if you want to do it for practice, you definitely are welcome to do it that way. But really what I would be looking for would be an approximated solution here of about 12.943. Okay, so as you work through your assignment, you might want to work through a couple of them and get exact solutions just to get the practice in with some of the advanced integration techniques. But keep in mind, I'm not necessarily going to require you to do that, at least on the ones that are more difficult, just because it just turns into an integration problem as opposed to focusing on the application of double integrals involving surface area. So I don't want you to get lost in all of that integration technique and lose focus on the big picture. Okay, so just kind of make your decisions as you work through the assignment. If it looks like it's reasonable to get an exact solution and you kind of see the technique right away, go ahead and try it. If you're not seeing it or you don't want to spend the time working on those integration skills, I totally understand, and just get the decimal approximations. That would be okay too.